So now let's talk about symmetric games. So players can in general be used to represent population. So the player is not a single entity, but rather a typical entity among a certain population of animals when we talk about biology, or a certain population, certain kinds of people, say people who do this or do that when we conduct a sociological analysis. In that case, mixed Nash equilibria can be seen as steady states of what is the average of those behaviors of various animals, people, and so on. Now, if you look at a single population, for example, a similar tigers who compete over some finite resource like land, or people who have equal roles. For example, you have drivers who arrive at an intersection and they all have equal options, equal roles, equal everything is equal approximately. Then we can model this by the symmetric games. Now, in general, symmetric games indeed models participants with equal roles. And the symmetric games in general are defined as follows. So game, I'm not sure, by the way, I think Dasgupta and Muskin didn't define that first, I think, but at least their definition is nice, because I don't find that one by Nash, for example, from 51 very simple, and I think that the complexity he has is not necessary for us. Anyway, so the definition is as follows. So given a game, it's symmetric. It's a game which is symmetric if all the players have the same strategies, and they in the way have symmetric utilities. What does it mean? It means that for every permutation of the players, so for every ordering of the players, permutation is a function which is injective and surjective. So it's a one-in-one and onto function. It means that it's a bijective. Injective and surjective means bijective from players to players. And so that for every permutation, and for every player, and for every profile, the utility of the player under that profile is the same as the utility of the result of the permutation under the respectively permuted profile. So if we look what is the utility of a certain player, it's the same as the utility of any other player when we rearrange the players in the same way that we also rearrange their strategies. So that the utility of a player does not depend on the names of the players. It only depends what are the strategies and in which order the player sees those strategies. So examples include prisoner's dilemma, rock paper scissors, rock paper scissors, not rock paper comma scissors, but rock paper scissors. I need to rock paper scissors. So the game, by the way that we saw on the last part, is not a symmetric game, because here if both players play football, for example, they have different utilities, despite the utilities that there is no difference between what happens besides the names of the players. So it's not a symmetric game. A symmetric game is when the utility of player depends only on the relative order of the strategies. So we have this definition, and then we also define what is a symmetric profile. A profile is symmetric simply if all the players have the same strategy. In particular, we can have an equilibrium which is symmetric. So an equilibrium is symmetric if, as a profile, it's symmetric. So an equilibrium where all the players have the same strategies. And of course, we will be asking, when do we have at least one symmetric equilibrium? Does having a symmetric game imply that we have at least one symmetric equilibrium, and so on? So now we have the simple version of this definition when we only have two players. So for two players, a game is symmetric if both strategies are the same, and the utility of player 1 under S1, S2 is equal to the utility of player 2 under the opposite utility. So when I act as 1 and the other person acts as 2, I don't care whether I'm 1 or 2. What player 1 gets when he plays as 1, the other person gets as 2 is exactly what player 2 gets when she plays as 1 and the other player plays as 2. And of course, when the profile is originally symmetric, so if 1 is equal to 2, then the utilities are the same. And as I said, that's why this game is not symmetric. The strategies are the same, but the utilities are different. The Battle of Sex is not symmetric. Okay, so the definition for two players is here, and of course the definition of a symmetric profile for two players is also that the utilities are the same, the strategies are the same. So first, for a finite game, we always can have a symmetric game, which has only symmetric Nash equilibria, such as the game in the example. It has only equilibria top left and bottom right. Or we can also have a symmetric game which has only non-symmetric equilibria. Here, only bottom left and top right. So for a finite game, we cannot say anything simple. But for an infinite game, we have the following proposition, which is actually an exercise from Osborne and Rubinstein, that when we have a two-person symmetric game and the strategies are equal and they are subsets of some Euclidean of some r-dimensional, some Euclidean space, they are non-empty, compact and convex, and the utilities are continuous and quasi-concave on the strategies, then the game possesses symmetric equilibrium. I remind that we have a similar theorem about the existence of Nash equilibria for two players, and here we only add the fact that we assume that we have actually the existence theory was for any number of players. And here we assume two players and we assume that they have the same strategy. And the game is symmetric. And then we conclude that the game possesses a symmetric equilibrium. And this implies, we'll maybe look at this at the tutorial session, but assuming this proposition, it implies that a finite two-person symmetric game always has a symmetric equilibrium. Not necessarily does it have only that, but it has always at least one equilibrium which is symmetric. How do we deduce that to that proposition? Simple. We say the following. So given a symmetric game on two players, the mixed strategy says they are equal, they are non-empty, compact, and convex. So the utilities, they are linear and they are continuous, being linear in the probabilities, and they also they're quasi-concave on this I. Well, we can show it, but now for the sake of time, we don't do it. As we did it for, I think we did it for the proof of the existence theorem of the existence of a Nash equilibrium in the mixed extension of a finite game. Similarly, we can prove that the utilities are quasi-concave on the side. Then the proposition above applies, and the proposition above says that, I remind you, it says that the game possesses a symmetric equilibrium. Now, what about a general number of players? Here we also have a nice theorem, the theorem by Nash. They are a bit different how we prove it, but pretty much the same. And the theorem says that a finite symmetric game always has a symmetric, at least one symmetric mixed Nash equilibrium. Now the intuition of the proof is as follows. The transformation which we use to prove that the mixed extension of a finite game always possesses at least one Nash equilibrium, in the second proof, the proof from the lectures of Ron Holtzman from the Technion, that transformation, or equivalently the transformation, that's exactly the same transformation that John Nash defines in his paper. That's actually the same. The proof quite closely follows that by Nash. That, when we look at it restricted to the set of symmetric profiles, it returns only symmetric profiles. So it can be seen as a transformation from the symmetric profiles to symmetric profiles. Now then, since the symmetric profiles are also non-empty, complex, and convex, the Brouwer's theorem implies that X has a fixed point, and since it's only on the symmetric profiles, this fixed point is not only an equilibrium, but also symmetric equilibrium. So let us do the details. Given a symmetric game, look at its mixed extension delta G when they have the same players. The strategies are the deltas, so the probability distributions of the strategies, and the utilities. I remind you that the expected values of the utilities in the original game. So consider the set of all the symmetric mixed profiles. So all the profiles in the mixed extension, which are symmetric. So P1 equals to P2 equals to the Pn. It's a subset in delta S, such that since deltas of S1 and so on till Sn are not empty, this subset is also not empty, it's also closed. Since if we have a sequence with all equal elements which approaches something in the Euclidean space, the limits are going to be also equal, because equal sequence approaching something means that each element approaches that, and if you have equal element-wise equal sequences, then they which converge, then their limits of course are equal. So the limit of such a sequence is also going, of any sequence in SP, will be in SP, because it's going to be a point in Rm with equal coordinates. And so it's not only not empty, but also a closed set. So let us recapitulate what we've proved, that SP, we define SP to be the set of all the symmetric profiles. Then we've proven that it's non-empty closed, and it's also convex, because for any lambda between 0 and 1, the convex combination of any two symmetric profiles is also symmetric. Because if P1 is equal to P2 is equal to tilde Pn, and P prime 1 is equal to P2 equal to tilde P prime n, then the convex combination of the P's and P primes also will give equal values. So delta, lambda, yes, lambda P1 plus 1 minus lambda P prime 1 is going to be equal to lambda P2 plus 1 minus lambda times P prime 2, because again the P's and P primes are equal to one another and so on, and equal to lambda P n plus 1 minus lambda P prime n. So it's a non-empty convex closed set ready to have Brouwer applied to it. But now we need to build and prove something on the transformation. So we now define the mapping from SP to SP as the restriction of the mapping from the set of all the mixed profiles to the set of all mixed profiles in the existing theorem. In the proof of which I said that proof that follows Holtzmann's proof, which is a variation on the proof of John Nash, of course. Of course, we cannot just define a function and says it goes to SP. We need to prove it goes there. So, because it can be that the restriction of a function on some subset goes beyond that subset. So we need to prove it goes there. So first, let us define that. We can say it's just a restriction, but it's easier for us to define it precisely. So from scratch. So for every point P in SP, so for every set of equal probabilities, for every player and for every J in the pure strategies set of that player, let, in the enumeration of the pure strategies to be exact, let P vector 2 as J denote the strategy profile when not a certain player as before, but each player I deviates to the pure strategy as J from Pi. So they deviate in the same way. Thereby, they keep the profile symmetric. Now define the following function for each J in the numbering of the strategies. And of course, the numbering is the same for all the players because we assume that strategy sets are the same. The GJ is the maximum addition to the utility because of this deviation to SJ of every n plus every player and 0. So if it's not a positive addition, we just take 0. Now, similar to what we did before, but now it's a bit different, so it's not, so it's a bit harder. We say that a profile is a mixed Nash equilibrium if and only for each J, the GJ in this profile is 0. So the direction that if you have a mixed Nash equilibrium, then the GJ will be 0 is clear, because you cannot improve by the definition of Nash equilibrium. The fact that they do it in parallel, the deviation does not matter, because the fact that they do in parallel, let me think 1 second, please. Actually, you know what? I think yes. 1 second. Oh, excuse me. They unilaterally deviate. So I now made it, I hope, clear. For every p, let p to its j denote the strategy profile when each player unilaterally, only that player, deviates to the same strategy. So we look at, okay, what is the strategy profile? Yeah, it needs to be better defined. So pi denote any strategy profile when a player unilaterally deviates to the pure strategy as j. So it does not matter from symmetricity which player deviates. So okay, I need to write it better. So for any vector, okay, for any vector, and for any strategy j, let p2 as j denote the strategy profile when some player, it does not matter which, because the result will be the same from the symmetry, unilaterally deviates to the pure strategy as j from the vector pi. So it's going to be the same, the same the same let me utility I from symmetry. Yeah, let me, so I apologize for the confusion. Let me now say it again. So having defined and found the properties of SP, the set of symmetry, of symmetric profiles, let us, for every point P and for any strategy number J, it says still MI, but every player has the same number of strategies, so it does not matter which I. Let P2 as J denote the strategy profile when some player I unilaterally deviates to the pure strategy as J from Pi. Now, these are all different profiles depending on which player we take. But it does not matter. The utilities will be the same from symmetry. And now define the following function for each J. The difference in the utility of that player, again, does not matter which player we take, and 0. So we just look at the difference if it's positive and otherwise it's 0. So it's well defined. It does not matter which player we look. We look only at one player, but it does not matter which. From the symmetry, this expression maximum of ui in p to s j minus ui in the original p and 0 will be the same. So we have defined GIP, and then the following holds. And now I don't have, not everything fits to the screen. I need to add again that the profile is a mixed Nash equilibrium if and only if for each j, GJP is 0. Why? If it's a mixed Nash equilibrium, then there is no way to change, so no player can deviate and change something, and therefore for each j it's 0. So that's the immediate direction. Now that direction follows from the fact that if for j, gj is 0, it means that no player can improve by unilaterally deviating to any pure strategy. And therefore, from the linearity of UI, we know that, well, the symmetry, as I said, it already is used to say that for every player, the utility from deviation will be the same. So from the linearity of UI, we can say that if no player can improve that from a unilateral deviating to any pure strategy, then no unilateral deviation to any combination, any mixed strategy can improve, and therefore we have that this is a mixed Nash equilibrium. So that's one. Second, that GGI continues because we look at a continuous change in the profile P, that we just make one of the players, does not matter which, but one of them exactly, one change to play as J, and then from the linearity of UIs and from the continuity of maximum, GJ is continuous. So we have defined GJ. We've said that GJ being 0 for all J's is equivalent to P being a mixed Nash equilibrium. GJs are continuous. So now for each player I and for each J, so number of strategy, of a pure strategy, we define Fij of point P, of strategy profile P, to be like we did before, only for one only for GJ and not GIJ, because the change does not depend on the player. So GJ tells how much a player can benefit from a change, and CA does not matter which player. So it's PIJ plus this benefit from the change normalized by the 1 plus sums of the benefits from the change. It's still normalization because we immediately get the following properties. For every player, the sum of Fij's P's is 1. Now, for every I and J, Fijp is non-negative because P's are all non-negative, GJs are all non-negative, it's non-negative. By the way, it's legal to divide by 1 plus the sum of GJs, because even if the sum of GJs is 0, it's never negative, so 1 plus is always a positive number, at least 1. Now, since GJs are continuous, as we said already, as proved already, Pij is a projection of P to what player I does to the probability player I gives to strategy J. That is as a whole a continuous function. So Fij is a continuous, and since we define Fij in the beginning of this SP set, which by definition is set of all the profiles which are equal for place, so P1 is equal to P2 is equal to till Pn, then we conclude that F1 is equal to F2 equal to till Fn for every j. Now, so let us say again what we have proved. We have proved the following. For every I, the sum of Fij's of all j's is 1, and Fij's are all non-negative. So Fij's go to the delta S. We also prove that for every j, F1j equal to F2j equal to till Fnj. So that goes to SP, not only to delta j but to SP, to the symmetric subset. So if you look at the transformation Fp, which just applies F11, F12 till Fnmn to the point P, then this transformation goes from SP inside SP. We can look at this only as a function from SP to SP. And since we proved that for any I and j, Fij is continuous, we also conclude that this transformation is continuous. So it's a transformation which goes from a set, which is, we proved that it's not empty, convex and closed, and this transformation is continuous. Therefore, by Brouwer's theorem, there is a point in this SP such that f of this point is equal to this point. That is the fixed point. Analogically to what we did in the proof of existence, if you need, just go to that lecture and take a look. The existence of a point P such that f of P is equal to P implies that for each j, Gj in P is 0, that, as we proved, is equivalent to P being a mixed Nash equilibrium. So we have proved that there is a P in SP, which is a mixed Nash equilibrium. But SP was defined as the set of all the symmetric profiles. So this P is a symmetric Nash equilibrium, which existence with non-constructively, admittedly, but still unequivocally proven.